can find it on the repository, which is on the screen. So I would suggest that, like last time, you first download the repository and try running an example, just so we can just set you up and make sure that everybody can run the examples. This time there will be basically one big example, and because I mostly wanted just to give you an idea of how one framework for deep learning works, and then I will explain better all the ideas through the slides. So if you have any questions on and problems while downloading this, just ask me or Bojan, and we will sort you out.
Which should we want to try it? Search file or?
The minst folder, train.
There is in MNIST folder file train MNIST solutions, which you should be able to run. And I mean, you should fill in the to-do still.
I think
train
you
MNIST.
that's
That's it. Just try to see if you can run train MNIST solutions.com.
Okay, let's start. So, as a brief recap, last 2 sessions we discussed supervised learning and unsupervised learning. We said that in supervised learning, we have that our machine learning system is exposed to experience, to a form of experience, which is expressed as a set of input and output pairs, and must learn to predict the output from the input. And what is expected from him is not only that he learns these and he memorizes these input and output pairs, but he's actually able to learn some knowledge which he can generalize to new inputs which he has never seen before. Within supervised learning, we basically saw 2 main subfields, which are classification and regression, which deal with predicting discrete and continuous labels, respectively. Unsupervised learning instead was a broader field in a way, because we saw that there are many different tasks that can be phrased as unsupervised learning. And the common idea behind unsupervised learning is to find some structure, some hidden structure inside your data, which can allow you to explain and understand better your data. So the two subfields we discussed were clustering and feature extraction, where clustering deals with finding subfamilies and subgroups within your data which are similar according to some metric, and how you define similarity defines in a way the clusters you will find and the structure which you will find. Instead, feature extraction deals with the problem of finding better representations for data. So your data in general is stored and represented as some multidimensional vector, and where each element of the vector represents some quantity of each data sample. In feature extraction, we saw that we can use methods such as PCA to find a better representation. So in the case of PCA, so that changing the reference system of your vector space, you could find a representation which was more suitable for example, as a pre-processing step in order to subsequently perform supervised learning. So deep learning. Deep learning is quite a hot topic within machine learning. The reason is that a lot of recent successes in machine learning were powered by deep learning. So the most impressive results in the last years in reinforcement learning, speech recognition, and image recognition, and the machine learning system behind many internet services which you use every day are actually powered by deep learning. The main concept behind the deep learning is to have a model which is capable of building hierarchies of representations, which can then be used to perform some task. So, in a way, a typical deep learning system can include both supervised and unsupervised learning, at least in the sense of feature extraction. So, a typical deep learning model will have several layers of transformations, which take the input, transform it in some higher level representation, which is fed to another layer, which in turn builds upon these representations to build higher level concepts and higher level representations. And finally, the highest levels in this stack of representations can be used to perform, for example, classification or regression or whatever task you're interested in. The most common model which is used to perform this type of hierarchical learning is neural networks. So neural networks have been around for a long time, and many of the ideas which have been used most recently to achieve these impressive results have actually been around for a long time. What's mainly changed is that it is only recently that we have the computational resources to experiment with sufficiently big neural networks and train them long enough in order to actually exploit the power and flexibility of this kind of model. So historically, the beginning of the fields of neural networks is in the 50s, when Rosenblatt proposed a model of a biological neuron in your brain, and he called this model, this very simple mathematical model of perception, and he showed that by updating the internal parameters of this perception, you could actually have it learn from experience, and you could have it learn to perform some very simple classification tasks. In the subsequent years, many people explored how connecting the many different perceptions into a neural network could actually be used to perform much more complex tasks than those which were possible with a single perception. In the 70s, however, the entire field of neural networks had what was called an AI winter. So Minsky wrote a very influential book called Perceptions, which showed a whole set of limitations of the specific class of neural networks which were being used at the times, and also the hype and expectations that had been put into this field were not met. And so for about 10 years, many people were quite deluded about the entire field of neural networks research. In the 80s, we had the first actual commercial applications of neural networks. So Jan LeCun deployed the first system for reading checks. So all the checks that are processed by banks all over the United States used a neural network to read automatically the numbers which were handwritten on the check. And this was one of the first major applications. However, it took a long time yet for these kind of models to be applied more widely. And because in the 90s, other kind of models, probabilistic based, such as graphical models, and other statistical methods were more suitable for the kind of resources that were available at the time. And it was so only since 2006 that actually neural networks came into wide use in the entire field of machine learning. And one of the reasons was that the availability of general purpose GPUs. So GPUs are graphical processing units. These are used to perform high performance computation on video processing. And in 2006, they were adapted in order to be able to perform general purpose computation as long as your problem could be framed in a specific way. And researchers realized that neural networks training was actually very suitable for this kind of hardware, which provided an incredible speed up. It can give you 1,000 times, can be 1,000 times faster than a normal CPU. And using GPUs, we're able to actually have some impressive breakthroughs in speech recognition, in image processing, and many different fields. So this is a perception. So this is the simplest component of most neural networks. A perception basically takes a set of n inputs, multiplies them for a weight, sums these values, sums the resulting value to some weight called bias b, and takes this linear combination of the inputs and transforms it using some nonlinear function. So you can use different nonlinear functions, but the basic mechanism remains the same within the single the single unit of a neural network. When you put them together, what you have is you have a graph that defines how the outputs of each neuron is seen by other neurons. So you could have that given your inputs are fed into a layer of perceptions, and in turn the outputs of each of the neurons in the layer is fed to other perceptrons, which take that input and transform it again. This is a very simple neural network. It's just one layer, one hidden layer with 3 nodes. But you could potentially repeat the same structure for many, many different layers. You could have hundreds of neurons in each layer. And you could have different types of connections. So in this example, every node is connected to every other node in the previous layer. So as I was saying, you can connect these perceptrons, these simple computational units, in many different ways, in very complicated structures. And if you have then a way of updating the weights of each of these neurons and updating the weights of an entire network simultaneously, which improves how well you're performing on some specific task, you can then, gives you a very powerful model. So the nonlinear functions which are used within each of these perceptrons are called usually activation functions, and they can have different shapes. So one of the most common in the 80s was the sigmoid. Nowadays are also used different types of activation functions, but they all have some sort of nonlinearity, which is what actually makes the model more powerful. Because without any activation function, the entire network would actually just reduce to a simple linear transformation. So it would just be a linear model, very, very simple and very limited in what you can achieve. But it's the combination of all these linear transformations with these nonlinear transformations embedded within the network that actually gives the representation power of the neural networks. So this is a famous example from Google. So they basically tried to build a huge neural network, and they fed it images from YouTube, and they basically trained the network just to recreate the image it was fed into at the beginning. And this forced the neural network to learn some representations which were useful to perform this task. So some highlight, and across the different layers of this huge neural network, the researchers realized that you could see very well what kind of concepts were learned by the different neurons. So at the lowest levels, you had these feature detectors which just recognize in the images things like shapes or edges, while at the highest levels you could have nodes that responded to faces and nodes which responded to cats, dogs, and all sorts of different concepts. And this is basically what makes the neural network so powerful. So this ability of building more complex representation based on the lowest level representation. So the first neural network I showed you was very simple. So it was basically just an input layer which just takes your vector of input of your data, and one single hidden layer which transforms the input layer and then feeds into the output. So this is what's called multilayer perception, and there is an interesting result that actually says that any function, so any function for regression or classification, can be approximated with arbitrary precision using just a structure like that. So a very simple structure with just an input layer, one hidden transformation layer, and one output layer. So this actually suggested according to many people, that there was no need to have very big and very complicated structures. But actually, more recent theoretical results show that although you can, in principle, represent any function using just one hidden layer, there is actually a benefit in using these very deep and very complex architectures. And the reason and the benefit that these architectures give you is that they usually require an exponentially smaller number of nodes. And each node is a set of parameters which you must train. So using a very simple architecture with just one hidden layer would most often require you to have a huge number of nodes on that layer. And so this will actually hurt the performance of your model, because it will be very difficult to train it effectively. So now we have these models which have all these parameters, and but how do you actually train them, and how do you actually get them to do something useful? So the first thing you need to define is the loss function. So loss functions encode what you care about. So the most common loss function, if we're doing regression, for example, is the mean square error. So this is the pink line. This just represents that if the correct label is 1, you have a loss, a penalty, which grows as you get farther from 1, either symmetrically on the right or on the left. Depending on your problem, you might have different things which you want to optimize. So you might not be interested in actually making subtle differences between this position here or this position here. For example, you might be interested in just having that if your label can be just +1 or -1, and you want to classify this, you might be interested just in being able to predict if the number is positive or negative, and then your loss function will actually not care at all about how far you are from 1, will just be 0 if you're on the right side of the 0, and will be 1 if you're on the wrong side of this line. So depending on your problem, you will have different ways of encoding what you care about, and this will have to be encoded in this loss function, which is what you will then try to optimize. So you will take your neural network and you will try to set the parameters inside your neural network in order to minimize the value of this function you have selected. The way this is done usually is most commonly is by gradient descent. Gradient descent is a very general technique within machine learning and within mathematical optimization, and basically identifies, given the values of your parameters, just select the direction, the direction in which you need to update your parameters in order to make your loss function decrease as fast as possible. And this you can compute just by computing the gradient of the loss function you are given for that values of your parameters. So what happens is that you start with some random values of your parameters. You compute the gradient of the loss function and the neural network. You take a step in the direction of the gradient, which is the direction of where the loss function decreases most fast. And then you reiterate this procedure. By doing many small little steps, you will eventually converge in some minimum of this loss function. One problem in this nice picture is how do you actually compute these gradients? So for a given value of your parameters, how do I actually know which is the direction which I need to update them in order to decrease the value of my loss function? It turns out that actually in the case of neural networks, this is not too complicated to do, because as we said, the neural network is mainly a sequence of transformation, so can be viewed as a sequence of as a composition of functions, where each function takes the output of the previous function and applies some transformation. And there is a very simple mathematical rule in order to compute gradients of composite functions, which is this equation which you can see here. So this equation might seem a bit not so simple, but it has actually a very nice interpretation which can be viewed very simply and which allows you to compute the gradients very nicely and very quickly. So what happens is that if you define your network, this is called a computational graph. The computational graph defines what sequence of transformation and operations you need in order to compute the output of the network. If you define the computational graph of the network, the gradient of the output, so the loss function, with respect to any of the parameters of the network, can actually be computed simply by multiplying the gradients of each individual transformation along a path and summing along all possible paths. So if you're interested in the gradient of the output with respect to this parameter here, you will just have to know how to compute the gradient of this transformation and the gradient of this transformation, and then multiply them. If you're interested in computing the gradient of the output with respect to this parameter of the network, you will need to know how to compute the gradient of this simple transformation, and that transformation. And then you will multiply along this path and sum this value with what you obtain by multiplying along the other path. So you have a very simple rule which you can apply in order to compute the gradients of your loss function with respect to any of the parameters of the network. So the only thing you actually need is to be able to compute the gradient for each of the individual components of the network on their own. But this is a much smaller and solved task in the sense that if you have a linear layer, this is very simple and you can find it just online. If you're interested, for any of the activation functions which are commonly used, you can find the gradient or you can compute it yourself. It's a very small and tractable problem. And it doesn't become more and more complicated just because you're using a bigger and more complicated network. Because you can always reduce it to a simple computation along paths on the computational graph. Interestingly, if you don't even want to compute the gradients for the single individual node, there is actually a way of computing gradients for the entire network without passing through the step of deriving yourself the gradients for each of the individual transformation. This can be done because any program, so any function in your computer, in your script that you write, can actually be reduced to a sequence of elementary operations for which gradients can be defined. And therefore, there are packages which implement what is called out-to-diff, which is a technique to actually compute the gradients of any program, of any neural network you are interested in training automatically. And these gradients can be computed with the same efficiency as computing the output of the network itself. So with out-to-diff, you can actually derive these gradients which you need to train the network for any network independently on the structure it has and very efficiently in terms of computational cost. So the most common, if we are dealing with regression, for example, the most common loss function we will use is the mean squared error. So the mean squared error is just the sum of the squared errors which you make when you try to predict the label for each of the inputs in your data set. So you have a set of input and output pairs, you take the input, you try to predict the output, and you will get some error. The sum of these squared errors, averaged, will give you this mean squared error, which is the most common loss function used for regression. Given what we said, you have a way to actually optimize very easily with respect to this loss function just by taking the gradients and following the gradients at each step and iterating this simple procedure. However, computing this function like this or other loss functions might be expensive if you try to compute it exactly. So if you want to compute the mean square error over your entire data set, and your entire data set has millions of data samples, you will need to make an entire pass through the network for each of these samples just to perform one single update. And you will need possibly millions of updates in order to actually get to convergence. So what is most commonly done is that mini batches are used. So instead of computing your actual loss function, the value of the mean square error is computed only on a small subset of data, sampled randomly from your data set. So you take a small subset of data, you apply your transformation, and you get your predictions. You compute the an approximate mean square error for that small mini batches of samples. You compute the gradients from that, and you apply your first update. And then you sample a new small subset of data and you iterate this procedure. In the limit, this can actually be leads you to what is called stochastic gradient descent. So in stochastic gradient descent, you actually make an update by substituting this mean square error over your entire data set with just the error on a single data point. So you take a single data point, you compute your prediction, your error, your gradient, and you perform immediately an update. Obviously, this is computing the error on a single data point as approximation for the error over your entire data set is a very weak approximation. But it turns out that it can actually be used in practice very efficiently. And because even though the quality of your gradients and the training signal you're using is lower, the implementation of stochastic gradient descent is very simple. And it allows you to parallelize across multiple machines if you have very easily. So even though you might need to perform more steps in order to reach convergence because your gradients are not as good, by parallelizing over maybe tens or 20 or 100 CPUs, you can actually get to convergence faster, even if your gradients are not as good. So the main advantage of gradient descent is what, as we just said, that it's easily parallelizable if you have a cluster of computers. It's also easily parallelizable on a graphical graphical processing unit. And it's very simple and in terms of both conceptually and in terms of implementation. However, there are some issues with this simple training algorithm. The first one is that you actually need to choose a step size. So the basic idea of gradient descent is that we choose the direction of where the loss function decreases as fast as possible, and we perform a small step. And then we recompute the gradient. The size of this step which you take may actually be relevant in order to ensure that you actually converge to some meaningful result. So if you choose your step size too small, it will take forever for your network to actually learn something. If you choose it too big, it might just diverge and become totally useless in performing whatever task you were trying to train for. And selecting the right step size for this is very tricky and might require many experiments in order to identify a good value. Another problem with gradient descent is what is called vanishing and exploding gradients. So if you have a big neural network with many different layers, the signal that comes from the loss function into the network tends to either vanish as you get farther and farther from the output of the network, or explode. So either you get a signal which becomes smaller and smaller and the lower layers of the network are trained too little, or you get a signal that tends to become too big and therefore it might lead to divergence of the network. So this is a very serious problem for training big neural networks with very big, with many different layers of transformation. But it can be addressed nowadays because with the kind of resources we have, you might just decide to have a very small step size in order to be sure that you don't make the network diverge, and then you just put on this on the training of this network a huge amount of computation. You can easily get on Amazon, on AWS clusters with 30, 40 CPUs, or you can get multiple GPUs. With this kind of computation, you can actually address even this problem, which was considered very serious in the past. Another issue of gradient descent is that by following the direction of where the loss function decreases faster, you're not guaranteed to actually arrive into the best values of the parameters. So because you just follow the gradient, you might get stuck in a local optimum. So you might arrive in a region of the values of your parameters, which is better than all the values that surround it, but is not optimal in absolute terms. And in which local optimum you might get stuck depends on the initialization. So you might, in order to get optimal results, you might want to run your training multiple times, starting from different values of the parameters, and try to see in which is the best results you can achieve. Another problem is what is called saddle point. So a local minimum is actually a point where you are actually stuck because all around you the values of the parameters are worse, and so the gradient cannot help you to get out of this situation. But there are also situations if you have a very high-dimensional data in which you don't have an actual minimum, but you have what is called a saddle point. A saddle point is a point where the gradient is 0, and therefore the gradient descent doesn't help you, doesn't identify any direction in which to move. But the point itself is not a minimum. So how can we address these kind of problems? One way is using what are called higher order algorithms. So in gradient descent, we are using just the minimum amount of information that we can. We just take the derivative, the gradient, and we just choose the direction of the steepest descent. If we use higher order derivatives, we can actually get better information. So what is called Newton's method is a different algorithm for optimization. While gradient descent just takes the gradient, the tangent to the current value, and it performs one step in the direction of the steepest descent, Newton's method actually looks for a more complex approximation of the function. So it looks for the best quadratic approximation of the function for the values of your parameters. And then selects the next point to evaluate by minimizing this quadratic function which it has fit locally to the data. this algorithm has several advantages with respect to gradient descent, but the main one is that you can avoid saddle points. So even if you end up in a condition where your gradient is 0 and your algorithm is not able, or very close to 0, and your algorithm is not able to effectively escape from this trap in parameter space, if you're using Newton's methods, you have additional information which I can tell you in which direction to proceed, even if the gradient is 0. The major advantage of using higher order algorithms is that computing all these higher order derivatives is actually very expensive in terms of computational cost. Even storing all the higher order derivatives might be too expensive to do. And so what is usually done is that an approximation of the higher order derivative is computed. So rather than computing the second or third derivative with respect to all possible variables, only a small subset of the derivatives are computed, and as an approximation of the full Hessian is used in the actual computation of the next step in your descent. I would say that at the moment, however, most neural network training is done with gradient descent and simpler algorithms. And the reason is as I said, that the amount of computation you can put on gradient descent being so simple to parallelize and so simple to implement, usually it's a better reason to use it than the limitation that we talked about just recently. So this is a basic idea of how you can train a neural network, but in order to train effectively a model to perform supervised learning or unsupervised learning using deep learning, it's not only important how you train the model, but also how you structure the network itself. So there are different architecture which you might use, different structures of the network, which will lead to very different performance depending on the problem. This is the multilayer perception. So this is the basic architecture for a neural network. You have your neurons, which are arranged in a sequence of layers, and each neuron takes as input all outputs of the previous layer in the neural network. The disadvantage of this model is that you have a very big number of parameters, and very often you actually don't need to have all these connections in order to perform well on the task you are interested in. So if, for example, you consider an alternative model which is called convolutional neural networks, convolutional neural networks allow to have to make a better use of your parameters and of your computation. So convolutional neural network, rather than connecting all the outputs of the previous layer to all the nodes of the subsequent layer, are arranged in such a way that each neuron only takes as input a small subset of the outputs of the previous layer. So if you have an image as input, you will have that, for example, in the previous layer, every neuron will only take as input a small subset of the image, and the different neurons will cover the entire image. This is useful because what you're doing is you're reducing hugely the number of parameters of your network, but at the same time, the type of structure you are assuming actually reflects some real properties of the data. So images have a form of locality. So in order to identify the object in a picture, you can compose it by just identifying at the first level small shapes such as edges, and then combine these edges into circles, into triangles, into more complex shapes. And so you don't need at each step to consider the entire image, but you can just recursively build onto small representations. And this was actually a major improvement in terms of neural network training. So most of the applications nowadays use, at least at the lower levels, these convolutional layers, which only take a small subset of the input. And actually only use the fully connected layers, such as the multilayer perception, at the last layers. So when he actually tries to build on all these representations he has constructed in order to perform the final task. Both this network, however, convolutional network and the multilayer perception, have an important characteristic, which is that they are what is called a feedforward neural network. So a feedforward neural network is such that the information only flows in one direction. So each layer only feeds into the subsequent layer. And the information flows monotonically from the input to the output. But this is not necessarily the case. So you could have, inside your network, you could have loops, and you could have more complex structures. And this is what happens with the recurrent networks. So in recurrent networks, you have an input, which is fed into the network, is transformed into some intermediate representation, and then, in order to predict the output, not only the current value of this representation is used, but also the value at the previous timestamp of that intermediate representation is used. So if you're processing, for example, sequences, and not independent samples, but you're processing videos or speech in which the samples you're considering are strongly correlated in their sequence, this gives you a sort of context which you can use to better predict the output. So if you're, for example, processing text and you want to predict the next word, if you, rather than just using the current word, you can also use the intermediate representation of the previous word. This gives you a better representation of your data and leads you to better performance in terms of this prediction problem. The problem with recurrent networks is that if your structure is cyclical, the simple pattern we have described before in order to train, which just multiplies along paths and sums along alternative paths, doesn't really work because you just have a cycle, and that simply cannot fit with the algorithm we have described. So what is usually done is that the network is unfolded. So you actually unfold the network and you build a bigger network and you feed the input at the different timestamps and you propagate all the information until the output. And this is called backpropagation through time, because you actually propagate the gradients which result from the current input into the values of the parameters of the network at previous timestamps. The problem with this scenario is that you are artificially increasing the dimension of the network considerably. And as we said, there is, when you're training with gradient descent, there is the problem of vanishing gradient. So training big and bigger network is difficult because the signal arrives very weak to the lowest layer of the network. And if you take your network and you unfold it repeatedly, you are making this problem even worse. So your recurrent network with special architectures, such as LSTM units. So LSTM units are special neurons, which are not as simple as the usual perception, but have a complex mechanism which allows them to remember things for a long period of time. The way they do this is that they have a memory cell inside, which can assume any value, and they have an input gate, which has a set of parameters which are also learned within the model just by gradient descent, which select when the input of the previous layers is stored or not into the cell. And when this cell is erased is also determined by another perception, which is also trainable within the network. And when the value inside the cell is emitted out as output to the next layer, this is also defined by a subunit within the LSTM network. Overall, what you get is a complex architecture that allows you to represent conditional statements, allows you to represent, to store information for long periods of time, and overall it significantly increases the flexibility and the power of your model. So when it comes to train your network, just selecting your architecture of the network and selecting a loss function is often not enough. So there are always an entire set of techniques which have been developed in order to allow to train efficiently and effectively your neural networks. One major issue when you deal with neural networks, which needs to be addressed, is overfitting. So when we discussed supervised learning, we said that the more complex the model which you're using, the more powerful it is, the more you are at risk of overfitting to your data points and failing to generalize to new data points. So even though you might perform very well on your training set, you might, the performance of your model on new data might actually be worse than if you had used a simpler and less powerful model. And this is actually a big problem within neural networks training because they are universal approximator. They are among the most powerful models which you can choose to use. They can represent any function. So you need to use specific techniques to avoid this from happening. The example in the repository addresses exactly this issue, and Bojan will tell you something about this.
So what you will do now is an example of a single-layer single-layer perception network. So the data set that you will be working with is the MNIST, which is like the classic data set to work with in like examples. The library for these neural networks, I mean there are lots of them out there, especially today for deep learning and for deep neural nets, like Tano, Caffe, TensorFlow, but they can be a bit tricky to set up and to use, depending on your machine and whether you use GPUs or a cluster of computers. So now we will use a framework called Chainer, which is, I think, quite simple to use, and it shows all the principles quite well. So this is loaded all the files in the MNIST folder from the repository, and this is the train MNIST.py file, which I will just briefly explain like what you have to do, what you have to fill in, and then I'll give you like 10-15 minutes to fill that stuff in and see for yourself how it works. So what I have set up is, like Matteo was explaining, you can have gradient descent, where you can have like mini batches of training data, and here you can set up the size of your batch. So at one gradient update, you take up here 100 examples. Number of outputs is the number of times we go through the data set, so it doesn't suffice just to go just once through the data set, so load all the data points into neural networks, update the gradients. What is much better is to do that several times, and here you can play with that number. And as said, this is just a single layer neural network, which means we have the input layer, the hidden layer, and the output layer. And this number here, it determines the number of hidden units in the hidden layer. Yeah, so now here we load the data set. Here you determine the number of the data points. This is the maximum that there is in the MNIST data set. Here you have to fill in the number of the sizes of your neural networks. So the size of the input layer, hidden layer, and the output layers. Here you have to, so we're now here in the for loop, which loops through the number of epochs. And for each epoch, you first update your parameters by a gradient descent in this part of the code here. So you take mini batches and you update your model here, and then you have to sum the loss of the loss for each data point in the mini batch. So multiply this is the average of the loss for a mini batch. You have to multiply it with the number of data points in the mini batch. And in the end, when you sum all the losses, so that if this is the loss over all data points, you have to in the end average it over the capital, which is the total number of points. So when you do that, we also do the evaluation. So we evaluate what is the test set accuracy and loss. So accuracy is the percentage of the data points that you got right. So data points for which you guessed what is a digit. And this is the value of loss you are optimizing. So, but this is now evaluation on the training set. So now you use test set. Also, you sum up all the losses and accuracies. You do the averaging, and then you print it, and in the end, you just print all the results here. So you saw there were a couple of to-dos. Those were actually the solutions, and you can also actually find them in the repository. But try to like fill in train mnist.py file with the correct pieces of code. And if you have problems, I just call and try to help. Yeah. Also, if there's something conceptually that you don't really understand, did anyone manage to, did you manage to run the script and get the, did anyone manage to, yeah. So the graph that you should get is something like this. So this shows, so if you did everything correctly, let me just go back. So this is the architecture of the network. So the input layer should have 784 input units, which is basically the number of pixels in the mnist data set. So I mean, it's 28 times 28, so in total that's 780 input pixels. This is the number of hidden units, which is actually a parameter which we change here. And the output is 10, because we have 10 possible classes, so digits from 1 to 9. And we have to decide basically between our network outputs the values, so the guesses for 10 different classes. So yeah, here we have done the permutation of the data set. So that is a kind of a heuristic we use, because I mean we can just go through the data set sequentially. So start from point number 1, 2, 3, 4 up to the number of points. But what turns out to be a good idea is to permute the data set so that your model is not biased towards any of the data points. So here you do permutation of 1 millibatch. Here, yeah, you just average loss and accuracy. Yeah, that's in general how it works. I mean, the main logistics of how model works is like hidden here, which is one learning step, which is done in the library, and that is everything that Matteo was talking about, like gradient descent, calculating of the gradients, updating the weights. Possibly even you can set up some other optimizations which can speed up the process. Yes, so in the end you see that how the behavior is. You can best see it on this graph. So the training loss in general with the number of epochs, that's basically the number of the amount of training you invest. The training loss always goes down, I mean almost always goes down. If we were to use the full gradient descent, so the gradient of the whole data set, then this training loss would always go down, because you always go down the gradient of the error function, so you always decrease the error function. But you use, here you use mini batches, so you take representation of the data set and then you update your training error. So, but overall, in general, it goes down. You would have very similar behavior even if you use a stochastic data set. You just calculate the error on one data point. And you can actually try to play with the parameters if you choose the size of the mini batch to be 1. So training error, training loss goes down. But you see with the test loss is actually the quantity we are interested in. We want that quantity to be as low as possible, because that represents how well did we actually learn, because we didn't learn on that test data. So you see that in the beginning it does go down. However, as you train more and more, it actually goes up, which is the sign that you're actually overfitting. So you are doing better on a training set, but you're doing worse on your test set, which means that your generalization of the model worsens. So you actually are not learning anymore. So that's also a problem. So not like, not just that your network is complex, too complex for the data you have, but also one network can be overtrained. So you training too much to fit to your training set, and then it just turns out that the behavior is worse as you train more. So there are also various ways you can deal with this problem. Like you can do some kind of early stopping. So you can say, okay, when I see that I have reached the minimum of the test set, test error, just stop there and take those parameters. Or other cases which Matteo will now explain. And also, just to explain, this plot here is the accuracy, which is actually the quantity we're interested in. So you can't really see well because this legend is in the way, but train accuracy in general goes up. Test accuracy kind of goes up and then a bit down. So it's difficult to know when to stop with the training, how many epochs to do, what is the size of the neural net. Now that you have this example working, you can very easily try to play with the number of the data points and see what happens. In general, less data points means less accuracy. You can play with the size of the neural network. So if you have smaller neural networks, that means that you're able to learn faster, but it is not as complex as maybe some network with more hidden units. Or you can have neural networks more layers, which you can also easily adopt in Chainer. And yeah, we can just play with the parameters and see how it affects. And now Matteo will continue with how to deal with other problems.
This part of trying different parameters is actually an essential part when you try to use neural network to perform any machine learning task, because there is simply no way you can just predict which is the exact best number of hidden units, the exact best number of hidden layer. You need to experiment and try to understand what fits better to your data. So that's a process that can be quite slow, because you might need to run multiple experiments in order to compare the results. And that is also one of the reasons for which you might be interested in trying some different model, which has fewer parameters, it's not so powerful, but maybe gives you just the best answer he can right away without requiring you to do as much experiments. So there's always a trade-off between how complex your model is, and therefore how much you need to tune it and tweak it in order to get it to work, and how simple the model is. Therefore it's easy to train, you don't need to run too many experiments, but at the same time you will probably not get as good performance as with a more powerful model. So in terms of overfitting, there is one technique which is particularly interesting. So besides just stopping your training early in order to avoid overtraining your network, another thing which is often done is called dropout. So dropout is a very simple idea, which turns out to be very powerful and very effective. So basically what a dropout layer does is There's just a layer inside the network which randomly drops, setting to 0, some of the outputs of the previous layer. So you can see this as cutting some of the connection randomly during training, and setting at each update, at each data point and minibatch you consider, you set to 0 a different set of nodes inside your network. It's not immediately maybe intuitively clear why this should help, but what happens is that basically at each time step selecting a random subset of the network, you enforce the network not to be more robust to noise. So the network must be able to must adapt in such a way that even if one of the nodes is set to 0, even if one of the pixels is corrupted, even if some random noise appears, the representation it learns must be robust to this. And being robust to noise is something which is good for generalization, and therefore enforcing this randomness and this noise inside your training data is a good way of actually enforcing this generalization to new data. Because in a way your data is always new, even while you train. So even though you are going through your data multiple times, the actual data which is fed into the network, the actual sequence of activation and transformation which are done, depend on these random dropping of units, and therefore it kind of forces the network to be more robust to this. And what happens though is that if you train your network with these sampled subsets of the network, the weights will tend to have bigger values. So when you at prediction time you use the entire network, you need to scale down the values of the outputs of each of the neurons inside your neural network by a factor which is equal to the probability with which you are dropping them during training. So last time we spoke about ensembling. So we were saying that often, even if you have some weak models, you can combine them by averaging their outputs, by do majority voting with their outputs and trying to put the results together. And we saw that this actually improved a lot the performance of many supervised learning models. You can think of dropout as also being doing this, because what happens is that we are averaging at prediction time all the possible subsets of the neural network. And this is actually very effective and very powerful. All these techniques which we discussed today have really countless applications. So especially big internet companies which have a lot of data which they can use and are investing a lot in deep learning, because when you have a lot of data, you can effectively use these powerful models and without the risk of overfitting. So all companies, big companies that work on computer vision, speech recognition, and these kind of very complex problems where you have a lot of data, but the problem itself is difficult, are using a lot deep learning. One of the fields which is using more these kind of techniques is computer vision. So computer vision is the field of computer science which deals with making visual tasks automatic. So problems such as recognize an object in an image, segmenting an image, which means identifying inside the image the different objects that are present, or compression, reconstruction, video processing. All these kind of visual tasks can be actually performed very well using deep learning. And the reason for which you might choose to use deep learning is that you usually have a lot of data, and the problem is, as I said, very complicated. So you have high-dimensional data because your image might be very big if it has high resolution, and there are subtle problems such as that the appearance of an image, of an object inside an image, changes, for example, with perspective. So it's very, very difficult to come up with a model that solves all these problems by hand. So just by writing an algorithm, therefore is often much easier to just use a very powerful and flexible model and let the model learn which is the best solution to the problem, rather than trying to hard code a solution to it. In particular, within machine vision, the model among the architectures we saw today, the most commonly used are convolutional nets. And the reason is that this, as I said before, the locality of the connections within your network reflects some property which is actually true for visual data. And so it's interesting this is an interesting visualization which shows what representation are learned by a deep neural network when applied to visual data. So what happens is that at the lower layers, these are the inputs, these are the weights of the neurons which take the image as input, so at the lowest level. So you see that these basically react to edges. So you have edges with different orientations, different curvatures, and at the higher levels, these edges are combined into shapes which resemble, for example, eyes or higher level shapes, which can then be combined into faces or cars or elephants or whatever is the content of your image. You can flexibly combine the lower level layers to represent anything you need. So this kind of hierarchical representation is a very effective way to compress a lot of information into very simple but powerful representation. So an interesting way of visualizing what is going on inside neural network was proposed recently by some researchers. So what they did was instead of trying to print the weights of each neuron and try to understand what he's reacting to, they tried to they made a feedback loop. So they fed an image into the neural network and tried to increase the strength of the pixels to which the neural network was reacting. And then feedback again inside the network the modified image and loop inside this neural network repeatedly in order to make all the patterns which the neural network is seeing into the image emerge and become stronger and transform the image repeatedly. And you can see that there is, if you look online, you can find these deep dreams, which actually show how these images can be transformed in very psychedelic ways. So you get that these clouds become dogs' eyes. It's pretty interesting because you see that the neural networks have an unexplainable fixation for eyes, for example. This tends to emerge in all the transformations. But it's an interesting idea to see what is going on inside the neural network. So depending on what you have trained the neural network on, the image will be transformed in different ways. So this was probably trained to recognize animals, and therefore that is what he tries to find inside the image. Another application, finally, which is becoming very common for deep learning, is natural language processing. So machine learning inside natural language processing is used for many different tasks, including translation, sentiment analysis. Sentiment analysis is the process of identifying if the sentiment expressed by a sentence or a document is positive or negative, but also is used for summarization, voice recognition, different types of analysis of textual data. And it's interesting that the same kind of ability, the same type of ability of extracting representation from data, which we saw for machine vision, so these edges which become images, which become higher order concepts, emerges also within textual data. So a tool which you could, if you are performing some natural language processing task, might be very useful is Word2Vec. So Word2Vec is this tool that transforms words into vectors. So it's how does this work? Basically, you feed this very simple and not particularly deep neural network a huge quantity of data, and for each word, to each word inside your data, the network assigns a set of parameters, which are trainable parameters. So when you will perform gradient descent on the network, these parameters will be updated. And the task you are trained the network to perform is to predict the neighboring words given the central word, or vice versa, given that the neighboring words predict the word in the center. And what you will see is that given that the representation of the word itself is a set of trainable parameters, while you perform gradient descent, the vectors assigned to each of the words in your dictionary will start to arrange into space in order to mimic semantic relations inside your data. So this is easily seen. For example, you consider the word Sweden and you get the representation which your neural network has learned for the word Sweden. You'll see that if you take all the words in the dictionary and you take the ones which are more similar in terms of vector representation, you actually have a nice set of geographical relations. So that the countries which are more close geographically actually turn out to have the most close representation also in terms of vectors. If instead you apply, so you learn all your representations, then you apply PCA just to reduce the size of your vectors to b-dimensional structure. And you map countries and capitals. You can see that basically most pairs of country and capitals in this vector space have the same, are connected by the same vector, by the same or oriented in the same way. This means that if you take, for example, the vector of Lisbon and you subtract Portugal and you add Spain, you actually get the representation of Madrid. So you have that the meaning and the semantic relations between words, such as quite a high order relation between countries and capitals, is actually encoded by geometrical relations inside your data. And all of this has emerged spontaneously just by the neural network looking into finding the best possible representation in order to predict the neighboring words. So this is I think, pretty impressive example of how the representation that the neural networks automatically extract from data can be actually very useful and very powerful, because they actually extract not only statistical and not particularly relevant information, but they can actually extract the real semantics of words and sentences. A final application I would like to just point out is that in most of the recent results in machine translation, so automatically translating from a language to another, are powered by deep learning. And they use this ability of deep neural networks to build good representations to perform the translation. So basically, many systems for machine translation now actually have two neural networks. One which builds a representation of the sentence in the first language, suppose English. And then the second takes the representation, the activation of the neurons inside the first network, and tries to decode this representation into the new language. And the fact that, so rather than passing directly from source to target, but just by translating one word at a time or doing some simple algorithm, by passing into some intermediate neural language, you actually get to much better performance in terms of translation. So this means that the representation which the neural network has extracted for the entire sentence is actually, which is just a sequence of numbers, it's just a simple vector, has actually retained all the semantic content of the original sentence, because using that single vector you are able to actually translate to the new language. And yeah, that's it. So, you have questions?
So when you say that you have more than one unit of the input layer,
Yes.
which one do you decide to feed? You've got an image.
So in the input layer you have one neuron for each of the pixels of the image, for example.
And is it was another thing like when word, where you select?
So in the case of the word, what you do is that the vector to each word in the dictionary you assign a vector, and the vector itself, so the set of numbers you assign to each word, is part of the set of parameters of the network. So it's trained during the process of gradient descent. So by trying to minimizing the loss in whatever task you are doing for natural language processing, the gradients also change your representation of the word until it becomes optimal to perform the task. And obviously, the bigger you can, and that becomes just a tunable parameters which you can choose. So you might want ideally you want very big complex representation which can encode very subtle differences among words. But obviously, the more parameters that you have, the more complex it is to train this model. So it's always about finding a trade-off in between having a representation of words which is complex enough to perform your task, but not so complex that then it becomes difficult to actually learn.
How do you use distributed computing with neural networks? Would you actually like distribute the network itself, or more like the loss function, estimating the loss function?
So there are different things which are done for applying distributed computing to neural networks. One thing you can do, for example, is if the neural network is really big, so each transformation, each layer of transformation is already a significant amount of computation, you could assign to a different machine each of the transformations. So while one machine is computing the second layer, the first one can already start computing the first transformation for another data point. But another thing, the most common thing which is done if your neural network is not too huge, is just use graphical computing unit. So this is a single machine, is a specialized type of hardware, which basically applies the same transformation, the same sequence of instructions to multiple data points at the same time. And this is exactly what you need while you're training a neural network, because you have a set of parameters, and you want to apply the same transformation to all of them. You want to take their value and sum the gradient. So this is exactly what you can parallelize really fast on a GPU. So you just, the graphical processing unit basically takes all of the parameters and in parallel updates them according to the gradient. Obviously, if your neural network is too big, the graphical processing unit will not be able to do the entire network in parallel at the same time, but will still parallelize the process significantly and can give you literally 100, 1,000 times speed up easily.
What's the name of that node that had memory, and is it widely used?
Yeah, it's LSTM units. They are actually quite used. So neural networks, recurrent neural networks, so this class of neural networks which have feedback loops, were considered very difficult to train, and but it's in the last few years they have started to be used a lot, mainly thanks to the introduction of LSTM units, which make the training much more stable.
Are there different architectures, such as that cell, that are coming out, and are there some theoretical limits to how creative you could get with these types of cells?
Sorry, could you repeat?
Are there new cells like that coming, on the market?
New architectures. There is literally no limit in terms of what you could do, and I think depending on the problems, there are often very specific architecture which are proposed, and I would say that most of the applications uses the basic components, so there are like 4 or 5 activation functions, the perceptions with or without a bias, and LSTM units, as I said. But new components are proposed all the time, and usually they try to address some specific issue which is most predominant in some specific domain. Yeah.
Is deep learning being inspired by brain sciences, or it's so it's trying to imitate the brain, the human brain, or it's just a similar thing?
It has definitely been inspired in the sense that the perception itself, which is the basic component, was proposed just as a mathematical model of the biological neuron. But at the same time, it's the complexity of your brains arises from the fact that it's just not one single neural network. There are different components which interact in many complex ways. The nature itself is something like backpropagation, but something else which we still do not really know. So I would say that this is definitely inspired, and people do use the brain as inspiration, but at the same time, you don't want to reproduce the brain itself, because it has a lot of constraints which may be due to many different things, just nature, random evolution. The fact itself that the brain is a structure where thousands of cells die every day and must be replaced, so must be highly redundant. There are many issues which you don't really care about, and many issues which you don't really understand. So It's usually an inspiration, but not a replica of parts of the brain.
What types of data can the deep learning techniques be used on? So you mentioned computer vision, which seems to rely on images, and NLP, which looks at text. But I was wondering about video and audio.
So it's used a lot for audio data, actually. So speech recognition, so take a registration of a person speaking and transcribe what has he said. This is usually using deep learning.
So is it transcripted first and then treated as kind of NLP?
No. The audio signal itself is fed into the neural network, and the neural network outputs the textual data. So because the fact is that as long as you have enough data to train a neural network, which is not always the case, actually, it's not the case very often, but if you have significant amount of data, the neural networks usually are able to find very good representation, as we said, and then whatever is the task you are trying to achieve, you might want still to use at least the part which builds these representations. So for example, for audio data and speech recognition, there are often hybrid systems that have at the base a neural network which learns these good representations, and then some other system which takes those representations and maps them to words. But I would say that it's not really about the type of data, but rather about the availability of data, which is the basic limitation when you try to use deep learning.
Okay, so it's not really used on video that much?
It's also used for video, but it's, I think this is it's very recent. So it's only since 2006 that people actually do deep learning, and so the first focus was on machine vision because many impressive results were being achieved. So now that machine vision is kind of well established, now they're looking to different things such as video processing, and video processing has all a number of very specific issues because you want to learn a representation which are not only useful on a single frame of your video, but have some kind of relevance temporally. So there are some additional problems which can be taken into account into your neural networks and are being developed at the moment. But I would say it's less mature than speech recognition and image processing at the moment. But it's definitely the next things that they are working on. Okay. Thanks for coming.